Okay, so in this video, I want to talk about volume using the washer method. So you should understand volumes by cross sections and then by the disk method before you watch this, because this is kind of just like an extension of those two ideas. And I have videos on all of that. Okay, so with the washer method's used with solids of revolution, but the solid has like a hole in it. So let's pretend I have this enclosed area here, so I want to rotate it. So if I rotate it, so think about what I'm going to get. I'm going to get this object. It's like this odd looking bowl shape with a giant hole that kind of has like a funneling hole through it, okay? But like the outside is kind of this like rounded shape. Okay, so let's just do a thought experiment here of what do the cross sections look like and why do we need something different with the washer method. So first of all, it's got a hole, right? So we need some way to compensate for the fact that there's a hole. But the other thing I want to say is, okay, so also think about like what's happening with the cross sections. So let's say I take this solid object, I slice it with a sheet of paper, I take a parallel plane or I take a plane of it. What does the cross section look like? Okay, so the cross section at this point, it is just, it's a circle, but it's got a hole in it. Okay, so here's my circle, here's the hole, okay? But now if I take a cross section down here, so I want you to appreciate the cross section actually looks quite a bit different in terms of like what's going on. This cross section has like thicker walls, right, than up here. The circle is smaller, but like also like the hole has gotten smaller because the walls have gotten thicker. So what's happening here is that the outside is changing and the inside is also changing. So when we take the volume, we just need to make sure that we kind of compensate for this change in the outside and the inside. So with washers, we need to know the outer radius, which is we're going to call big R of X, and then the inner radius, which is little r of X. Okay, so the formula for volume by washers for rotation about the x-axis, it's still just the formula for the volume of any cross section, but in this case, the particular formula is going to have pi, and it's pi because it's a circle, so pi is always involved with things that go circle or spherical, so pi is always involved. But check this out. You take the volume, you take r squared of really that. So you're taking, sorry. Okay. You are taking the volume of the outer shape minus the inner shape. So this is actually what's allowing you to get that hole in the object. So if I go back to my original just solid here, so if I just were to take capital R squared, that would get me the outer shape. And then by subtracting the volume of the inner shape, that's what's actually going to bring into account that we have the hole. So you can kind of think about why this formula makes sense. Okay, so I have a few examples in this video to go through with you guys. This is kind of the key formula that you're going to need to know, so I would make sure you have it written down if you're not doing my guided notes. So find the volume of the solid generated by the enclosed region about the x-axis. I know I've got a typo in there, sorry. I type some of this stuff out sometimes just to save my handwriting. Sometimes this is a lot of writing for my hand. Okay, so I've got y equals x, y equals 2, x equals 0. Okay, so I hope that if you've been learning about this, you know that you cannot do this if you don't have the illustration. Okay, so here's the situation. I've got y equals x, y equals 2, and x equals 0. So what's the area that is enclosed? It's this little area in here. And so then I need to rotate this around the x-axis. So I rotate this around here. So think about what this shape is going to look like. It's going to look something like this. So I've got these like straight walls on the outside, and then I have like this cone shape in the middle. So again, I have something happening different from the outside versus the inside, right? So this is why we want to use that washer formula. Even though I don't have like a perfect hole maybe all the way through, it still kind of acts the same because I have something on the outside and then something on the inside going on. Okay. So looking at this, so kind of comparing the two, this part here, which is this curve, y equals 2, that's the outer radius. And then this curve here is definitely the inner radius. So I think that drawing the actual rotation is going to help you to label what the initial picture is, because once you understand this, now the rest of this comes together pretty nicely. So now I'm gonna just bust out my formula. So I've got pi times big R squared minus little r squared. And okay, so this, just to reframe everything, so this is the outer, so this is capital R, this is the inner, so this is little r. And then I also just went through and I labeled my points of intersection, which you're often gonna have to figure out so that you can get your limits of integration. Okay, so now I can just really plug and chug everything in. We said that big R was this curve here, so 2. Little r was this curve here, so that's x squared. So I just plug it all in, and then this goes from 0 to 2, so bada bing, bada boom. Okay, and from here, now it's just a matter of doing the algebra. So if I work this out, so I'm going to bring the pi out. This just comes out to being 4 minus x squared, and then I can go ahead and integrate. So I've got 4x minus 1/3 x to the third. Of course, that's multiplied by pi, and then I can just plug in my limits of integration. So I will now just, here's the rest of the work. If you are trying this example, you can just make sure that it came out to this, but this is what I got in the end. And you can pause the video if you want to write down or review any of the work. Okay, so this is the basic idea, okay? So now let's change it up. And let's find the volume of the solid generated by revolving the enclosed region about the y-axis. And I didn't tell you the formula for y, but really you just switch everything to y. So if you've been working with the disk method, then you should know how to switch to y. I talked about that in my other video. Okay, so now I've got x equals tan y equals 0, x equals 1, and y is between, this should say y is between 0 and 4 over, or pi over 4. Okay, so what I want to encourage you to do is, this is a challenging graph maybe to think through. Oops, I still got a typo there. Okay, this is a challenging graph to think through. Maybe it's not to you. But I do want you to pause the video and try to actually draw this whole thing totally on your own. You really have enough information to kind of sketch this out. And this is the whole thing. So if you don't spend the time practicing this, then you're never going to get better at it. So if you just watch me do it, you're not going to get better. So I recommend you pause, hit play when you're ready. Okay, so let's think through this. First of all, so one thing I always suggest is if you are struggling because we've flipped the x and the y, you should know your base graphs. And so the base graph of just y equals tangent of x looks like this, right? So if I flip-flop my x and y, I'm going to have a graph that goes this way, right? And okay, so that kind of gives me a general idea of the orientation for the graph. So the next thing I would recommend is that you plug in these points here, 0 and pi over 4. And remember, so this is what y can be. So I have at 0, so if y is 0, then x will equal 0, so tan of 0 will equal 0. And then at pi over 4, so if I plug in y equals pi over 4, then x will equal 1. So make sure that you're just oriented the right way. So that just helps me get to the curve. You know, no stress with that. So one thing that's always helpful is to plug in the two bounds. If you have bounds, that's a really good way to kind of help you muddle through the graph if you get stuck with it. Okay, so I also need to include my x equals 1 and y equals 0 as I've got here. So I can see then here's the little enclosed region, and I'm rotating this about the y-axis. So it's a shape that looks like this, where I've got these walls and then I've got kind of this like hole shape, this cone shape going in on the inside. And from this solid, right, so I can see what's my outer versus my inner curves. So that's going to help me decide how to set up my function. So the outer function is this line here, this is the x equals 1 line, and then this inner function here, that's tangent of y. Okay, so now I can set up my equation. And I need to make sure now this is all in terms of y, right? So I'm not working with x's anymore, so you just have to flip your orientation. So I said that the 1, x equals 1 was on the outside, tangent of y right here was on the inside, and then this is going, you can see, from 0 to pi over 4. Okay, and so from here, now it's just integrating. And I wouldn't say this is like the easiest integral to do, but, you know, in ideal world, you know, this would be the so-called easy part if calculus were easy. So let's go through the integral. This simplifies then to solve, I'll just pull the pi out. So 1 minus tangent squared y. I think what makes this tricky is that you can't integrate this as is. So you've got to bust out this good old trig identity that secant squared minus 1 equals tangent squared x. You've got to use that. So if I make that replacement, as you see here, then I can rewrite this whole integral as 2 minus secant squared y. And this I can integrate, right, into 2y minus tangent y. And then it just comes, it's just a matter of plugging in my limits of integration, which I will go ahead and do. I have run out of space here, so I'll just tell you the final answer will come out to pi squared over 2 minus pi. And that's because, right, so 2 times pi over 4, that's going to give you pi over 2, and then don't forget to multiply by this last pi. And then tangent of pi over 4 is just 1, so multiply that by pi, so there you go. Okay, so that's an overview. If you are interested in more examples, I have another example video. If you found this helpful, please consider liking or subscribing to the channel, sharing with some friends, or leaving a comment. I always appreciate that. And I will catch you guys in the next video. Thanks for watching.